Okay, this next review module video deals with everyone's favorite topic, significant figures. Feel free to print off the associated PowerPoint presentation as well to follow along. This topic is not covered extensively in the Harvey e-text, but I thought it was an important thing to touch on as we begin the semester. Alright, so let's talk about Usain Bolt. Alright, freakishly fast athlete. Set the world record, obliterating it a couple of years ago. Alright, the time we saw reported on the Olympics, 9.58 seconds. Alright, it would be true to say that his time was 10 seconds within rounding, but of course that's not very helpful because within rounding, everyone runs 10 seconds at the Olympics. Alright, it would also not make any sense to report to this many digits because obviously even at the Olympics they don't have a measuring device that accurate to measure to that many digits. Alright, so we see 9.58 because that's reflective of the accuracy of the device. Okay, because all measured quantities, whether it's time or whatever we're dealing with, is always uncertain. All measured quantities are uncertain. And so what the sig figs do for us, they tell us the degree of uncertainty. That's what they express. Okay, and so that's why we need to keep those in mind when we report quantitative values. Okay, so let's go ahead and take a look at some different measured values. Alright, on this first yardstick, or meter stick I should actually say, we're dealing in centimeters. And so this one has no divisions at all except to the nearest centimeter. Alright, so we know for certain that the measurement is 4 centimeters. Okay. And so that is for certain. Alright, whenever we make a measurement, we always report also one uncertain digit. So I could maybe approximate that this measurement here is, say, 4/10 of the way between 4 and 5. So we'll call it 4.4. Okay, so we have all our certain digits and then one uncertain digit at the end. All right, and we could report that with an error bracket, 4.4 plus or minus 0.1. We're within that range. Okay. All right, and this is how we report the uncertainty for all our measurements, reporting all the certain digits and then estimating one uncertain digit. All right, the second centimeter reading, this one divides to the nearest tenth, not just to the nearest one. So I can know for sure that this measurement is 7.9 something. So those digits are certain, and so we approximate our uncertain one. So I'm going to say that this is about 6/10 of the way between 0.9 and 8.0. So we'll call it 0.796. Okay, so we have all our certain digits and then one uncertain digit. Okay, and so that's the appropriate amount of sig figs our measurement should have. And this one I might not even be certain to the nearest hundredth. I might say plus or minus 0.02. Okay, and so the error should always be in the same decimal place, in the hundredths place, as that last uncertain one. Okay, we can look at a couple more briefly for some other types of measurements. Here we have a pressure gauge, and so we can see for certain this goes to the nearest ones place, so it's definitely 21 point something, so those are certain. And I'm going to say the needle is just past the 21, so we'll call it 21.1 pounds per square inch. Okay, with our one uncertain digit. Alright, likewise with our temperature reading, it goes between 28 and 28.1, so we're sure that it's 28.0, and then we'll approximate the uncertain digit and call this, say, 6/10 of the way between 0.0 and 0.1. Say 28.06 degrees Celsius. So always getting all our certain and our last uncertain. And so that's how we deal with all measured quantities. All right, also a couple things to keep in mind. When we have digital readouts, for example, from a balance or from the Spec 20s, we always have to record all those digits. We assume all the digits from those digital readings are significant. So even if the last few digits are zeros, we know that the balance does measure out to the nearest 10,000th place. So make sure to record all the numbers given by your electronic readings. Okay. All right, you recall the good old guidelines for using sig figs. Of course, all digits besides 0, always significant. Zeros at the beginning of numbers are not significant. Zeros in the middle of numbers are. So this number would have 4 significant figures. All right, again, the 0 being in the center of the number, we'd have our 3 significant figures. All right. At the end of the number, zeros are significant if there is a decimal place in the number. And so in this case, there is a decimal place, so these zeros would be significant. So we'd have 4 total. Here, the zeros are at the end of the number, but there is no decimal place. And so these zeros are not significant, so the number would only have 2 sig figs. All right, but say we did want to express 5,600 with 4 sig figs. Well, one way we could write it is 4,600 and just put a decimal point at the end. That looks a little bit funny, but that would correctly express that these 2 zeros are now significant with the decimal place. Okay, so that would express the 4 sig figs. A clear way to write that probably would be in scientific notation. So 5.600 times 10 to the third. Okay, indicating all 4 of the digits now are significant. Okay, so basic rules for sig figs. And then, of course, when we're dealing with calculated quantities, not only do our individual measurements have to have correct sig figs, but also the values that we calculate from them do as well. All right, so for addition and subtraction, we're limited. The key factor is the number of decimal places. Okay, and so adding these 2 numbers together, we can punch it in our calculator, we get the final value. Okay, the first number here only has 3 decimal places. The second one has even 1 fewer, just 2. So because we're limited to 2 decimal places, that's the least out of the 2 we have here, our final answer also will be limited to the 2 decimal places. All right, and so we'll have to round this off at 15.79 because that 2 is not significant. All right, so addition and subtraction, always think decimal places. Multiplication and division, we're concerned about the actual number of sig figs. All right, and so here we had 2 sig figs in our first measurement, multiplying by something with 4 sig figs. All right, so whichever is less will limit our answer. So 2 sig figs, so our final answer can only have 2 sig figs. And so we would have to round this off at 40 point, okay, indicating those 2 digits. Okay, so let's go ahead and take a look at applying these calculation principles. All right, so for this first example here, we're dealing with just calculating a molarity from a measured mass. All right, and so we can do the math here and take our 0.2331 grams, divide by our molar mass, so 1 mole is equivalent to the given 151.16 grams. Grams cancel and we have moles. We want molarity moles per liter, so we'll divide by the volume, converting the milliliters to liters, so 0.0500 liters. Okay. We can crunch this out and do the math, and we come out to 0.0308415 molar. Okay. And so how many of these numbers are actually significant? Well, all we're doing here is multiplying and dividing. And so we'll be limited by the number of sig figs. So here we have 4, here we have 5, here we have only 3. So our final answer will be limited to the 3. And so we'll round off to 0.0308 molar. Okay. Also, one thing to highlight, when you're using molar masses, because the periodic table goes to so many decimal places, we never want that to limit us. So make sure your molar mass always has more sig figs than any of the other numbers in your calculation, because we don't want to introduce a limiting factor if we don't have to. All right, in the second example, an analysis has been performed, and we're going to calculate the percent error. All right, so of course the percent error is the difference between the actual value and the measured value. All right, and so our actual value was this first number, 0.1621. So we'll take the difference between the student's measured value, 0.157. Okay, and percent error is usually written positively, so we'll include the absolute value just in case it came out to be negative. And then we take the difference as the ratio of the true value, 0.1621. Okay, and then times 100 for the percent. Okay. So here we have a mix. We have a subtraction and we also have a division. All right, and so we have to remember our math rules for order of operations. All right, and so since this is all together in the numerator, we have to do that subtraction first. Okay, and so when we do this, it comes out to be 0.0051. Okay, but we have to look at our sig figs. Here, remember for subtraction, we focus on the decimal places. So we have 4. Here we only have 3 decimal places. So our number from this calculation in the numerator comes out to 0.00551. But we'll have to leave off that 1 because it's not significant. But if we do leave off that 1, then when we divide it, that's going to introduce a little bit of error. And so one way we can keep track of the 1, because we do actually want to include that in our calculation, but we know it's not significant. So write it as a subscript, okay? And so we'll take this and divide by the denominator. Okay. And so we can calculate this out and come to a final value of 3. Okay. And because this only has one significant figure, even though we're using the 1 in the calculation to avoid a rounding error, we know it only has the 1 sig fig. This one has 4, so our final answer will be limited to 1 sig fig. And so if we wanted to keep track of those other numbers beyond that in the calculation, we could, but if we write them as a subscript, that indicates that they're not significant. And so that's a good way to keep track of the other numbers without indicating they're significant when they're really not. Okay. All right. Let's look at one other example dealing with that issue of rounding errors. All right. So here we have 3 different numbers, and basically we want to take and report the average. All right. And so these are the numbers the student calculated on their calculator. But after analyzing their data, they determined that each should have just 3 sig figs. Okay? And so again, when we do the math to calculate the average, we want to include all the decimal places, because if we round off too early, it will propagate some error in our analysis. But we want to recognize that even though we include all the numbers in our calculations, they're not significant. So again, write the non-significant digits as subscripts. So for the first number, we'll take 9.94734 because it only has 3 sig figs. Okay, we'll add the next number, 10.0. Those are 3 significant digits, and then the rest are not. And then lastly, 9.87, 3 significant, 0.38 not significant. Okay, and to get the average, we'll add them up, divide by 3. Okay, and so now when we do the math, we'll include all these non-significant digits so we don't have a rounding error. And we can crunch that out to come to 9.94827. Okay, and then we can look back and analyze. Here we're doing addition, so we're limited by decimal places. So here we have 2 significant decimal places, 1 and 2. So the 1 significant decimal place limits us, and our final answer should have 1 decimal place. And so we'll round to 9.9, back to our original units, nanograms per liter. Okay. And so by keeping track of the non-significant digits, it allows us to use them in our calculation, but without getting mixed up in the significance. Okay. All right, one last thing, sig figs and calculations. One other type that we encounter, for example, when we work with pHs, is logarithms. And they have kind of a unique rule for sig figs. So the number that we take the log of, in this case 1.09 times 7 minus 4th, it has 3 sig figs. And the rules for logarithms indicate that our answer, the number of sig figs in our original number, should equal the number of decimal places in our answer. And so we would round this to negative 3.962. So kind of unusual, a mix of the addition and multiplication rules. The number of sig figs in the original number is the number of decimal places in the final answer. Alright, so last rule for logs. And one last thing to consider when we're dealing with extremely large data sets. Okay, so here's a bunch of numbers, and typically what most of us have learned in school, when a number ends in 5 and we need to round off, we round it up. Anything below 5 gets rounded down. So we'd have, if we needed to round these to the 10th place, we'd have 4.1, 4.2, 4.3, etc. All right. But think about this, if you had an extremely large data set with hundreds or even thousands of values, and you rounded every number ending in 5 up, that would end up artificially inflating your data if everything always gets rounded up. So one technique we can use to avoid that from happening is if the number ends in 5, round to the nearest even digit. Okay, so if we round up here, we go to 4.1, which is an odd digit. And so if we round the other way, if we round down, that would get us to an even digit. Okay. All right. Here, if we round up to 4.2, that's even, so we'll keep it that way. Here, if we round up, that gives us 4.3, it's odd. We need to round to the nearest even digit. So 4.2 will round down. Here the rounding comes out even, so we'll keep it. Here it comes out odd, so instead of rounding up, we'll round down. Okay, so we come to 4.4. All right, and so you can see by using this method, half the time we round down, half the time we round up. So when you have a large data set with many values, it won't be artificially inflated by rounding up every time, because half the times we've gone in the other direction, rounding down. Okay. All right, well, this concludes this review module video. And next you can take a look at the homework problems associated with this on Sapling Learning.